Auto-white balance plays a crucial role in rendering accurate colors in photographs. Most auto-white balance algorithms assume a single dominant light source in a scene. However, real-world environments often contain mixed lighting conditions. Applying single illuminant auto-white balance in these cases usually results in poor color correction. When auto-white balance corrects only the indoor lighting, the result has a bluish tint. In contrast, correcting only for outdoor lighting results in a reddish cast. By blending the two corrected images could produce a more balanced result, capturing both lighting conditions. Unlike traditional auto-white balance that are constrained to a single illuminant per scene, recent methods propose rendering multiple sRGB outputs with fixed white balance presets. These methods then use a lightweight model to estimate a blending map for each preset. Once the blending weights are computed, each pixel is linearly combined to form the final output. At this point, we asked ourselves two key questions. Is linear blending the most effective way to combine different white balance settings? And are current datasets truly suitable for training and evaluating multi-illuminant white balance methods? To explore the first question, we analyzed the white balance presets more closely. For the second, we created a new dataset tailored for image fusion white balance correction. To visualize preset limitations, we select three random points in the image and plot their RGB values. Next, we construct the convex hull formed by the 5 fixed white balance presets. In theory, for linear blending to succeed, the desired white balance values should lie within these convex hulls. But plotting them as crosses, we see that they often fall outside the hull, showing that linear blending is inherently constrained. To quantify this, we compute the percentage of pixels in the rendered white balance dataset that lie inside the convex hull, only a 0.24%. For the ground truth pixels that lie outside the convex hulls, their average minimum Euclidean distance is 8.13. To overcome this limitation, we propose a simple and efficient non-linear method to blend the 5 white balance presets. First, we concatenate the preset images and project them with a 3x3 convolution. Then, we apply a transformer block followed by an unprojection layer to produce the final sRGB output. To ensure efficiency, the transformer operates in feature space with channel-wise attention. Our model has less than 8,000 parameters and runs in under 200 milliseconds per image. To address the lack of suitable training data, we repurpose the LSMI dataset. This dataset contains raw images of scenes captured under 1, 2, or even 3 different illuminants. To create the ground truth for multi-illuminant images, we follow 3 steps. First, we compute the white balance corrected single illuminant image using color checkers. Next, we apply auto-white balance to the multi-illuminant version of the same scene. Finally, we adjust the per pixel brightness of the single illuminant image using the multi-illuminant auto-white balance corrected. Note that we only use auto-white balance for brightness adjustment, not for color correction. Our method achieves state-of-the-art in our dataset, but also in a cross-camera setup, in the synthetic test set, and in a single illuminant setup. Please refer to the paper for detailed quantitative results. As discussed earlier, fixed white balance presets alone fail to correct color cast in mixed lighting. Other methods like deep white balance and mixed white balance also struggle to remove this cast. In contrast, our method produces cleaner results, bringing white walls closer to the ground truth. In summary, we show that white balance pixels often lie outside the convex hull formed by the white balance presets. we introduce a more effective, non-linear method for blending white balance presets in multi-illuminant scenes. And finally, we propose a new dataset for training and evaluating fusion-based white balance correction,